it out. So how do you actually get started? So the first step is to get your odometry pods. And after you get that, you would want to go to learnroadrunner.com to start actually like learning how to tune your robot.
And tuning your robot. What tuning your robot is, tuning makes your odometry more accurate, and it allows you basically to use trajectories or to control your robot during the autonomous period to let it know where it needs to go. And what tuning actually is it's taking the output of your odometry pod, the information that gets sent to you, and slowly bring them closer to the actual position you are on the field, so you can see where you are clearly. Odometry pods will give you inaccurate readings, or at least readings that aren't exactly the same as where your robot are in real life. So you do need to tune them until it can be close enough to be actually used on a field. Tuning does take a long time and is different for every robot. The main thing that you're going to be tuning is drive constants. What that is just details about your robot, how long it is, or how fast it goes, the gear ratio of your motors, and your wheel radius, things like that. But the most important thing to remember during a tuning session is that you should always double check and triple check, going back to test your robot over and over, because a lot of things can change.
So any questions? Also, one more opinion about this year. As we've all seen, like I'm pretty sure the FTC kickoff was 2 weeks ago. Yeah, 2 weeks ago. And like odometry this year, since you have to go over like the pipes to get to the warehouses, odometry is probably not going to be as useful. I don't think in any purpose whatsoever you're probably going to need to use it in anything but autonomous, and even in autonomous its use is going to be quite limited. So yeah, it's not as useful this year, but it's a good thing to like learn and maybe have prepared for other years.
Okay, thank you very much, team 18175. So next up, we have team 16072, Quantum Quacks. Philip from team 16072. He's currently employed at a machine vision implementation company, and he's here to share with us Opencv image processing. Welcome, Philip.
Howdy, and I should move outside in just a second. We're setting at the table, so I won't put my mask on. But let me pull up my presentation. Yeah, so I'm going to be talking about Opencv, which is super cool software. Share screen, there's the button. Okay, can you all see the slides?
Yes, we can.
Cool deal, thank you. So I'm going to talk about, and I believe there's a table set up for me now. So I am sliding out. You can just wait till they actually call you. No, they just called. I'm presenting right now. It's all good. Okay, so y'all should be able to hear me better now. Okay, so Opencv, let's do this in the order that I said I was going to. I will ramble too long if I don't. So here's what we're going to talk about today. We're going to go through who I am. We're going to talk about computer vision. We're going to talk about color spaces. We're actually not talking about kernels anymore because I was going way too long. I can rant about kernels for years. Then we're going to talk about what Opencv is, what Easyopencv is, what Easyopencv Sim is, and then we're going to walk through a simple duck pipeline. So we are going to try and speed run this as fast as possible. If at any point during you have a question, feel free to throw it in the chat or unmute and holler it. I will be going fairly quickly because I'm trying to cram all this in a short period of time. I will have some times where I pause specifically for questions, but feel free to shout it out. You don't need to wait till then. Okay, so who am I? Like you said, I'm on Team Quantum Quacks. We're from Cary, North Carolina. This is going to be my 3rd year of FTC and my 4th year as a machine vision intern at Fourth Vector Technologies, which is a machine vision integration company, which is a bunch of fancy words, but it basically means I do this for, well, I guess not a living because I'm a teenager, but this is what I do for work. So yeah, and I'm gonna put, if you have any questions about Opencv, feel free to add me on Discord. That is my Discord tag. There's 2 N's. And I'll come back to that at the end. But okay, so what is a color space? So color spaces are kind of the fundamental of computer vision and how we think about things, because a computer doesn't understand color. All a computer knows is ones and zeros, on and off. And so somehow we have to turn a combinations of ones and zeros into color. And so we have these things called color spaces, which is how a computer thinks about color. On the left here, we've got RGB. That's the one, if you've done anything with color before, any digital application, anything like that, you've probably used RGB. It tells you the amount of red in an image, the amount of blue in an image, and the amount of green in an image, or pixel, I guess. And so this is normally 000 to 255, 255, 255, or if you're doing hexadecimal RGB, 0 to FF. That's just a way to tell the computer, okay, and that's how computer screens work, is it's got 3 LEDs. It's got a red one, a green one, and a blue one, kind of, not really, simplification. And that tells it how strongly to turn each one on. It's pretty cool. But the problem is, if you have a little bit of change, it can vastly change these numbers. I had an example that I was going to show, but I lost it. So, oh well. But if you have a slight shift in color, these numbers vastly change. So it's really hard to do any kind of looking for a color in RGB space. The other really popular one for computer vision, and I know there's a bunch of others, there's YCRCB, there's Lab, there's YUV, there's all sorts, but I'm only gonna talk about RGB and HSL because those are the 2 most common. HSL is what I would recommend everyone use for computer vision. It, instead of being a cube, it's a cone. And so we start building the cone. We have our color wheel. This is oversimplification. This is going to be better. Here we go. So this is H and S. So H is the angle that you're at along this wheel. And then S is how far out along this wheel you are. So how saturated you are. And then we turn it into a cone by adding lightness. So no lightness is pure black, pure lightness is pure white. And then you've got your ranges in there throughout your hue spectrum. You can look this up. Wikipedia has some good stuff about color spaces. There's a lot of good resources because it's something that we need to deal with all the time. So if you want, you can just look up what are color spaces or how to distinguish between color spaces, and someone will do a much better job than I did because I'm not very good at explaining stuff. There's a thing in the chat. Reminder, yes. Amazon gift cards, very nice. Okay, so Opencv. Opencv is a library for computer vision. It is incredible. This is used in industry. My company uses Opencv. It's used for hobbyist projects. It's used for everything. basically any computer language that a sane person would want to write a computer vision application in, they have a version for. So they've got Python, they've got Java, they've got C++, they've got C#. Those are the main ones that people use. The important thing to note there is if you're using it for Java, because you're doing it for FTC, you want to make sure when you're Googling like questions, like, oh, how do I find the average color of a region or something? You want to make sure to include Opencv Java find average color of region, or else you could get the Python, and the libraries are a little bit different. Okay, so then Easyopencv, what is that? If you've heard that name, or EOCV, Easyopencv is an implementation of Opencv for FTC. Opencv is free. It is an open source library, so if you are super into computer vision, you can actually go and contribute. If that's something that you're passionate about, go for it. But yeah, it is free. So is Easyopencv. Easyopencv is, and here I've got, no, that's the sim. Here it is. This is the easiest way to install Opencv onto your bot. It supports basically everything you could want to do. And all you have to do to install it, if you've installed Roadrunner or if you've installed Dashboard, this is going to look very similar. You go and add this to the build Gradle file, and then you put a single, you put a file onto your USB storage. Yes, I will share the slides afterwards. You need to put a file onto your USB storage, but that's not particularly difficult, and they've got steps to walk you through all that. And that is what I use. That is what I would recommend everyone use, because otherwise it's just a pain to try and get it all, and it takes 7 years to download, and yada yada yada. So then Easyopencv Sim is a tool for building pipelines. It lets you make pipelines without having a robot or a field with you, which is really nice for people like me that unfortunately do not have enough room in their bedroom for a field, or enough money to put a field in their bedroom. And so I can just take a picture at a workspace, and then when I get home, I can work on trying to process it. Okay, so I've got one pause for questions now. After this, I'm going to switch to talking about detecting ducks, and then we're going to pause for questions again at the end of that. And I don't know, how much time do I have left? How speed running have I been?
You have pretty spare time. You can go on. Good amount of time.
Okay. Cool. So whenever I start to look at a pipeline, can Opencv be used to detect where you are in the field? So yes and no. You can, there's not a built-in method for it. There's not a built-in method for anything. Easyopencv, which is what I was showing off here, it supports doing Vuforia and Opencv at the same time. So if you wanted to use Vuforia to tell where you are in the field, you could do that through Easyopencv. If you wanted to do a little bit something more advanced, you could write your own pipeline to do location tracking. Quantum Quarks is planning on having our own pipeline to do location tracking. And if you have any questions about that, feel free to DM me, but it's pretty complicated, so I'm not gonna go into it here. It requires, our solution requires a lot more depth than I feel like is important to share. So yeah, so for the duck pipeline, we're detecting it at the beginning of auto, right? So the things we know where the robot's gonna be, because we're gonna put it in the same spot every time. We know where the barcode's gonna be, because it's required to be there by the game manual. We know what color the ducks are. We know what size the ducks are, and we know where our camera is. Okay, so that's a lot of information. Whenever you have that much information, that means your vision stuff is going to be really easy. The less information you have, the harder your vision is going to be. So the only thing we need our vision to figure out is which one there's a duck in. Really straightforward. So I'm going to show using the Opencv Sim because I'm too lazy to buy a capture card. Sorry. I'm going to show what color space conversion, a representation of it to help kind of get that in brain. I'm also going to show how to do it in Easyopencv. I'm going to talk about drawing rectangles, submats, means, which we'll understand what these mean later on, and then a way for you to pass this value back out to the rest of the code. So before I dive into the code itself, let me share this. Okay. This share. Okay. So this is what Eoncv Sim looks like. So you can tell here I've got 3 pictures of ducks. And so I'm going to use this to test my pipeline. And if we look up here, I've got some other pipelines going on. Here's a grayscale one. That's a color space that is kind of a weird color space because most people don't think of it as a color space, but it really is one. It just doesn't have any color in it. So this is going to be our RGB color space. And I'll go ahead and show this off so that people kind of see where we're heading. But so this is what the final version of our pipeline is going to look like. So you can see it puts a yellow box around the duck. And yeah. So the way this works, is there a way, I forget how to do this in Zoom. Show all windows. Advanced. There we go. Nope. Screen right there. Okay. Because I'm going to be flipping back and forth between 2 applications. Shoot, this is not the one I want. Don't worry about that. I cannot see because it's so bright outside. Is there a way for me to turn up my brightness? No, there is not. Okay, I'm at full brightness. That is fine. So if we come and we open up my, gosh, I really cannot see. That's this one, ducks. Okay. So, just kind of do the, so does everyone know how to do the yes on the reactions in the toolbar? Yes, no, slow down, whatever. Okay, so let's use that. And if you have done a decent bit of Java code before, put yes. If you're kind of new to this whole Java thing or are unsure about it, put no. Cool. So I will explain what some of this Java syntax means at the same time. So instead of coding this from scratch, I'm just going to walk through this pipeline. I could code it from scratch, but I'll end up making more errors. And for explanation, it's just going to be less useful. So up at the top, we have our import statements. These are very important. Without it, your computer doesn't know where to go find things. If you're using Android Studio, once you put Opencv in your Gradle, then it will automatically handle importing for you if you do tab complete, which is really nice. So then, yeah, so we start with our class, which is how Java breaks up its files. So our class is called duck location final, and we need to extend something called Opencv Pipeline. And Opencv Pipeline is how Opencv does its thing. And you need to extend that so that you can call methods involving it and stuff like that. You can look up what inheritance lets you do in Java. Gosh, the sun's really bright on my face. Whatever. You can look up what inheritance lets you do in Java, but if you don't have this extent, it's not going to work, and it's going to be unhappy with you. So then we start by defining some rectangles. And these point values, so this is X, Y, width, height. And I just kind of tuned those. Like I was like, okay, I want it to be centered around that duck. So like, for example, I'll make the first slot move over a good bit. When I click back over here, see how it's now shifted over. The important thing to note about Opencv is, like most, oh, there we go, a cloud running over the sun. Like most engineering stuff. Can you all see my cursor?
Yes, we can.
Okay, cool. So this top left corner is 0, 0 in the coordinate space. So to go over, we go positive. To go down, we go positive. There's no such thing as negative coordinates for an engineering or image processing stuff. So just make sure you think about that, because most people assume 0, 0 is the center, because that's what makes logical sense. But engineers are so special, they need their own coordinate system. So we have 0, 0 being here, and going down doesn't go negative, it goes high. Like the larger the number, the further down it is. So it's kind of confusing at first. Once you play with it a little bit, it makes more sense. And that's why I recommend drawing the rectangles, which I'll show how I did that later, because that lets you kind of look at your image and be like, oh, I did the coordinate system wrong, because I do that all the time. This is something called a constructor. Yeah, where do you get the Opencv simulation? I can put, I'll put the, I will put this link on my slides when I talk about the simulator. And then when I share my slides, you'll have the link. Fine. You're saying I've got low resources. Die. Okay, that's just because I'm running Java, I think. Okay, click in here. Come on. There you go. So that's the link on how to get to it. And they have all the installation instructions on their GitHub. So then, yeah, we have this thing called a constructor, which lets us pass stuff to it. Get slot selected. So you'll notice we have a variable that we've declared up here, slot selected. And I initialized it to -1, so that if you ask your pipeline for where a duck is and it tells you -1, you know the pipeline hasn't been finding it. So this is how you would ask your pipeline for where it thought the duck was. Then we get to probably the most intimidating part of this, but once we walk through it, it should make more sense. This method called process frame. So this is the most important part of any pipeline, because basically what it's going to do is it's going to take your map, is what they call them. It's basically an image. It's going to hand it to your process frame. The process frame is going to do its magic, and then it's going to spit back an answer. So, and I'm actually going to start, I think this will be cool. I'm going to comment it all out and then uncomment it a little bit at a time. So we start out and we're going to just convert it from RGB to HSV. Hello. Load. What is wrong? What do you not like? Come on. Well, it didn't like that. I don't know why. So we're going to undo that. But
So Philip, you have about 1 to 2 minutes to, left in your presentation. If you can just wrap up and start the questioning process, maybe.
Sounds good. So yeah, so the meat and potatoes of this. So we convert the color. That's CVT color. Then I blur it which you don't really need to do, but it's nice to do. Then we create our rectangles. So this is the code that actually puts the rectangles on the screen for us to see. Then we do something called submat, which splits our image up into smaller images. And we decide that based off of our rectangles. Then we do the mean or the average of each subimage. And then we take the hue. And then we come down here and we say, okay, if space 1 has a larger hue, because when I looked at it in the telemetry, see how I print out the colors? It looked like wherever the duck was had a higher hue, because otherwise it was black. And with yellow there, it's going to be a higher hue. So then if spot 1 has a higher hue, then it's 1. If it's 2, then it's 2. And if 3 has a higher one, then it's 3. And then I also drew it again in green just to make it really easy for people to see. Yeah, so the questions. I sped through it. I said I would give y'all this link. So there you go. I just realized that that link gives you edit access. So let me change that real quick. But yeah, so what questions do people have? What is the best way to learn how to use Opencv? That is a great question. So there's a ton of resources. Can any camera? Yes. Legally, you can only use UVC cameras that are plugged into your control hub. So you can look at the resources that they give you in Opencv. Here's tutorials that Opencv has released. So here is a set of tutorials. They are going to be for Eclipse. You don't want to do it in Eclipse. Follow the setup instructions for the sim instead. And if you're confused about any of that, you can DM me, and I put my Discord on here, so you can DM me there. Does this pipeline allow live view for the driver? So the new update 6.0, so for 6.0 was ultimate goal. That disabled live view during run method. So it allows live view during a knit. You just click on your thing and say view pipeline. But you can't have it live while you're either running auto or running teleop, because they said that was a safety hazard. Who created Opencv? It's a community effort. They do have an official website. If you just go to Opencv, opencv.org. This is their official website. They've got some documentation on here too, and they talk about all sorts of stuff that they've got set up. My Discord was not entered correctly. Okay. That's exciting. Let me see.
Thank you so much, Philip, for your presentation. That was awesome.
Thank you.
I enjoyed it very much. So there might be more questions flowing through chat. You can answer them through chat, and we're going to move on to the next one. Thank you so much.
Good.
Okay, so next up, we have team 1827 Area 52. Everett will be presenting about TensorFlow model training. Everett is an 8th grader from St. Mark's School of Texas, and this is his 2nd year in FTC as a programmer. He'll be showing us how the robot processes it and learns data that is presented with. Area 52 placed high in Texas Cup last year as a semifinalist during their rookie year. Welcome, Everett.
Okay. Share my screen. Okay. I hope everyone can see this.
Yes, we can see it.
Okay, I'll start now. So hello, my name is Everett. I'm representing Team FTC 18227. Today I'm going to talk about TensorFlow object detection. So the basic plan of my presentation today is first an introduction to TensorFlow, then I'm going to get into some details of coding, and then just show a quick demo to illustrate all of the code, and then just share some lessons that I've learned. So what is TensorFlow? TensorFlow is an open source library developed by Google for building machine learning and artificial intelligence models really easy and convenient. And it mainly focuses on deep neural networks, which the three branches that I'm most familiar with are image classification, object detection, which I'll be using today to illustrate the use of TensorFlow and FTC, and then semantic segmentation. So to illustrate those three branches, I have some photos of dogs, because who doesn't like dogs? So with image classification, it's kind of like the name. You'll feed the model an image, say like the dog on the right, and the model will say, hey, this is a dog. Or like if you feed it an image of a cat, the model will say, this is a cat. But with object detection, you can feed it something like the image on the left, and they'll draw a bounding box and say, hey, there's a cat right here, and there is a dog right here. And with semantic segmentation, it's pretty interesting because it predicts class labels for every single pixel in the image. So the result is something like a very fine and precise outline of the dog, and then a very good outline of the cat as well. So some of you may be asking, oh my gosh, FTC already provides their own TensorFlow model. Why would I need to take the trouble to train my own? Well, first of all, a custom trained model offers so much more flexibility because, for example, if FTC, well, this year their model has balls, cubes, ducks, and markers, you could detect objects such as the carousel or your team's own custom object, for example, like a cone. And also, pre-trained models may not work well in diverse lighting and positioning conditions and shown in past seasons, because last year in Ultimate Goal, the rings that we were detecting had to be centered and in perfect lighting, but in like reality, it's pretty much almost impossible to make everything perfect when it comes to the team's own field or a competition field. Okay, so now I'm going to go through the code for the training and implementation processes. So as a first step, you need to collect a lot of images for your custom labels. So I collected for my model about 200, 300 images of balls and cubes in
Everett, are you still here with us or did you drop?
He probably dropped.
Yeah, it looks like he did. So while we wait for him to come back, I'm going to make my short announcement that's going to be happening before the drawing. Before our next presentation. Oh, Everett's back. Hello.
Oh.
Okay.
Okay.
You may keep on going then.
Okay, well, my Wi-Fi just was terrible. Okay, let's start again. I hope you guys heard this part. So I'm not sure when I left off, but I'll just restart on transfer learning. Okay, so transfer learning is basically adjusting a pre-trained model to detect your custom labels, and it's often said that transfer learning can, 200, 300, okay, sorry. Well, okay, so a TF records is basically a TensorFlow recommended format for reading data of your images. And the label map is basically just a list of all of the labels or custom labels that you're going to be using. And then, okay, transfer learning, I've already said, adjusting a pre-trained model to detect your custom labels. It's often said that it's faster and produces better results since it's based on an already pre-trained model. And then you need to deploy your model on an Android device, which I'm going to get to later. So this is the basic interface of labeling your images, because you can't just directly feed the images to the model in object detection. So in the middle is a photo screenshot of label image. That's what I use to draw bounding boxes around images so the model could use them. And it'll export XML files, which are the screenshots on the left and the right. And on the XML files, let's get the pen, okay. It'll show like the name of the label that you're detecting. When I took these screenshots, I was working on another project regarding eyes. So, and then they'll also output the coordinates of the bounding box that you just drew. So that should be very helpful for the model. What's happening? Okay, let's just use this. Bang, and then this is the actual output that command prompt will put out while you're training. You can just notice that most notably here, we just have the time it takes for the model to run one step in training. Okay, so some issues that I had in training were first making the TensorFlow scripts accessible. They were first in this weird .proto format, which we needed to convert to .py. You can use Google's protobuf to convert them. And then also along the same lines, when I was debugging, also you can find a bunch of online resources that can help with this. I just put labeling images and running transfer learning here since I had some problems with those as well. And yeah, let's move on. So now to make the model actually tangible after we're done with training, we need to export it as a PB. And this is pretty important. You need to export it using export tf-lite graph tf2.py, or else TensorFlow will have problems converting it to tf-lite and they'll be very unhappy with you. So this is a problem that I ran into when I was exporting it. I used tf.savemodel.save, which I said on the side, it doesn't work because it is not exported in the correct format. So when you're putting it and trying to convert it to tf-lite, it just won't work. And last year's FTC SDK is not compatible with TensorFlow 2. It was only compatible with TensorFlow 1.10, which was pretty inconvenient. But this year, it is compatible with TensorFlow 2, so that is very good. So next, I just put down here, again, I'm emphasizing finding the correct code to export the PB file is very essential. It's very important. If you don't find the correct code, the TensorFlow is going to be very mad at you. Okay, so for your convenience, I've just put the converting code right here. I've left some parts out, but you can find that on the TensorFlow website. If you just search up on Google, like TensorFlow convert to PB, to TF-lite. There's other options on the TensorFlow website. Another common one I've heard about is using command prompt, but I just used this one and it has worked fine for me. And next, we are going on to deployment on the FTC robot controller. So first, you need to copy the pre-written FTC program called Concept TensorFlow Object Detection, or I think there's a Concept TensorFlow Object Detection webcam if you're using a control hub, I believe. And then so you first need to copy that into the team code folder, and then move your converted TF-lite model into the assets folder. And the next three steps are basically replacing their parameters with your own to make the code compatible with the custom trained model. I think I'm a bit short on time, so I won't get into those, but they're on the slide. Okay, now we're gonna get into the demo. Yay. Video. Okay, so this is just not running on the FTC robot controller. It's just running on my computer, and it's detecting the cube and it's drawing a bounding box around it. If you'll notice during like some of the movement, it'll misdetect it as a ball, which is a result of not having enough training images, which I fixed, and now it is working fine. Okay, now it detects the ball, and wait for it. Okay, there we go. This is what makes it kind of distinct from image classification, because it can detect the cube and the ball in the same frame, which is important. Okay, here are some screenshots that I have. This one is basically illustrating how to implement an FTC robot controller. We've replaced the, I don't know if you can see my mouse, I'll just use this. We've replaced the their preprint model of ours in the assets folder. We've also changed the name of the model that we'll be using, and we've also changed the labels as well. And these bottom 4 images are basically just illustrating the model in action. It's pretty reasonable accuracy, I guess. 83% is not bad, but you can see I can detect it when it's far or close. And of course, there are alternatives to tackling this issue of detecting balls and cubes and maybe ducks. And with Opencv is a very common one. There is definitely less room for error because, well, when my team's using Opencv, we use filters in an app called Grip instead of an AI model. So in case you're not careful and you may screw up your images a bit, Opencv will be fine. But as of my team's experiences, we've had a bit of trouble to detect the white ball because there isn't a particularly distinctive color to it, unlike the orange rings and the yellow cube. And also, as I've touched on before, the FTC provided TensorFlow model is one that you can definitely use. It is convenient. If you're careful, it can yield pretty good accuracy, but again, the lighting and positioning must be perfect, which is a con. So now I'm just gonna share some lessons I've learned through this process. Firstly, training. I've learned to take advantage of all of these online tutorials. I mean, if you're doing a project too, if you have a problem, Google it. Okay, and then with TensorFlow model building, one extremely important thing I've learned is converting PB to TF Lite. I spent like a ton of time on this and I was searching through all of the errors and I couldn't find anything because in the beginning I hadn't exported it in the correct format, and that's pretty bad. Also, my third lesson is patience and resourcefulness can be very helpful. So with patience, you can't expect to get a project right the first time. As I liked to think about it, when I was frustrated, everything that could go wrong was going wrong, and that was pretty reasonable expectation because a lot of errors will pop up that you will not have accounted for. And resourcefulness is also a very important one. As I've touched on a ton of times before, just take advantage of all of the online resources out there because chances are people will have encountered similar issues. I don't know what happened with my slideshow there. And yeah, so that's the end. Thanks for your attention. That concludes the presentation. And I'll take questions if you don't, well, if you want to email me or my team. The emails are right here. And yeah, I think there are some questions in chat about me sharing the presentation. It is a PowerPoint file. I am not sure if I can do anything about that, but I mean, I guess I could just post a file. Not sure how to do that. Okay, well, I'll do that afterwards if I can give some room for other people to present. Oh, saved as a PDF. Okay, sure. I'll look into that. But if there aren't any other questions, I guess I can turn it over back to you, Shulko.
Okay, thank you so much, Everett. So now before our next presentation, I'm gonna have a quick announcement. So this is about the giveaway that's gonna happen after the next presentation by Iron Ring. Make sure to put your team number behind your name just to be automatically entered for our first giveaway, a $25 Go Builder coupon and 2 Gecko wheels. And I'll be taking a screenshot of the participant list while Iron Ring is presenting. And also at the end of this track, we will also be having a giveaway for $25 Amazon gift card. Anyone who have asked at least one question will be entered once. And that's it. So next up, we have Team 6832 Iron Rain, and they'll be presenting about the universal team shipping element. Welcome.
Can you hear us all right?
Yes, we can see the slideshow.
All right, wonderful. All right, so we are Team 6832 Iron Rain from Dallas, Texas, and today we're going to be presenting our universal team shipping element. I'm Ben.
I'm Cooper.
I'm Sean.
I'm Trey. And I'm Mahesh.
Okay, so when designing Ftc, we had to consider the basic design requirements, including the official sizing and materials, and it had to be stable, stackable, durable, and then we had to make it easy to grab in place. And we want this to be available for all teams to use, so no 3D printers required, backwards compatible, and easily discernible.
This is our solution to those problems. It's called Ftc, kind of like Ftc. On the next slide, we have a promo video. It's like 40 seconds long. Go. Lost in reality. So a cone is a very obvious shape to use as its wide base makes it easily stackable and easy to place. Yeah, not all cones are legal or stackable or very stable. So this is why we're proposing a common geometry. And this allows teams to retain flexibility and the chance to make their Ftc unique and ensure that they can earn the full 30 points. So why should you use our specific geometry? So we've made over 30 different cones testing various sizes and stackability to arrive at our current geometry. And this geometry ensures that the cone won't rest on the shipping elements while being able to withstand some iron rain level driving. This is the current geometry that we have. It is a 4 1/8 inch tall cone with a 3 7/8 inch wide base. And keep in mind, this is only our release candidate, and hopefully this geometry will stick as the community tests it. Our goal is to have the community make different variants of our standard. So in order to do that, the variants should be compliant with our size. And if you're using magnets, there are a couple different things that you should comply with magnets. So, there should be 4 magnets, and there's certain polls that you have to look at. Make sure you go to our GitHub page to see that. The variants, we have some posted variants, such as we have flats for the gripper and magnets for extra pickup. You saw some of those clips in the promo video. That's on our GitHub repo. We have some samples here. See, this one has the flats. It's got hyperbolus. Yeah. So again, we fully encourage teams to embrace their creativity and only suggest that they use our templates as a reference if they are unable to manufacture their own. Here are some designs contributed by Dr. Michaud, and he let us use them in our presentation.
So we just ask that once you make your design, there are 3 simple steps that we want you to do to make sure that it complies with our standards. So as long as it nests well with the basic cone geometry, as long as there is clearance between, once you put it on the shipping hub, as long as there's clearance between it and the level 3 cargo, as even though it's not a penalty, it might as well be. Since if it's not supported purely by the shipping hub, then you do not get the points for it. And just test it rigorously. I mean, give it what you got.
Okay, so in order to ensure that all teams can use FLYSET, we've prepared various ways to manufacture it, including paper templates, cutting machines, and also the 3D printing. Okay, so on our GitHub repo, we have our flat pattern designs as PNGs, SVGs, DWGs, and the PDF. We encourage teams to take a look at these, print them, and modify them to benefit their own needs. Okay, so this is our 3D reference model, also on our GitHub repo, and teams can print this and test it out with their robot in order to ensure that it's compatible with their own designs or to add on to it with different variations.
So like mentioned before, teams should embrace their creativity and ingenuity while still maintaining compatibility. We have manufactured a couple different designs. Here's one with our team number on it. And here's some with different hyperbolas and some with magnet tabs. So there's a bunch of different ways to make your own FLYSET unique.
So when it comes to detecting a FLYSET during Auton, teams are going to be responsible for developing an Opencv pipeline or TensorFlow model to do that. If there are enough teams that request a TensorFlow model, we're down to develop one and release it publicly. We're going to actually have a talk right after this one where we go in depth as to how you can prototype a vision pipeline as well as use it practically on your expansion network control hub. And so, yeah.
How you can participate. So there are different levels of participation. We have the people who formally adopt the standard. We call those our signatories. The people who adopt it early before final release. Promoters are the people who are sharing it with other people. And then certifiers, those are the people who are testing our models and making sure that we have good designs and that they work well with other people. Yeah, next slide. We also have a drop height challenge going on. Basically, the challenge is that we want you to drop your model from the highest point possible. Here's our little example. The highest point, I guess, gets clout. Bonus points. Good for you. Be safe. Yeah. Please don't like jump out of a plane and drop it or something like that. Yeah. But before we get into any questions, I want to talk a little bit about our timeline. So we're presenting release candidate 1 to you today, and we're targeting the final release about 4 weeks by now, or about 4 weeks from now, towards the end of October. We're going to make changes based on community recommendations, but again, we expect the overall geometry to stick. So we're now open to questions. Wow.
Yeah.
No questions, huh?
Right then, if I might just add in, we're talking about obviously all this community integration. If you adopt the standard and you have feedback and you want to share it, please do. Obviously, this is looking to try and be a universal standard. So if you have places to post and share it with, obviously with respect and all.
Okay, there's a few chat questions. So would you recommend using magnets or not? This is up to you. We thought magnets might be an easy way for a gripper to hold or pick up one of these. This specific cone here has 4 magnet pockets that have been pretty much soldered on. This is made out of plastic. It was cut on like a cricket machine. And here's a stick that has a magnet built in. You see, it's just another way for teams to pick it up. It's completely up to you whether or not you want to use it. Would it be possible to make it out of a flexible 3D printing material? So we actually printed one out of nylon. This is a base mode print. It's only 1 wall thickness, and it took about an hour to print. And nylon's pretty flexible. You can see this one's pretty squishy. It's easy to pick up. It's pretty durable. Again, if you have a claw that like has a death grip and like squeezes it to death, you know, you may not want to use a flexible filament, or you may want to use a flexible filament. Again, it's up to you.
In terms of printing out with TPU, I'd say that it would be tough, but I think it would be doable.
Mm-hmm. Again, the standard that we are proposing is just the geometry. As long as it has some way to be picked up by other forms of grippers and stack, then you know it's fine. It works.
Another thing to note is for that TPU, it's pretty slippery. Might be kind of hard to grip. You'd have to have something that either has a death grip or something that has really grippy grippers.
Yeah, really grippy grippers.
But again, if you have an idea, test it.
Mm-hmm.
Barrett.
Tag us.
Any more questions? That's it.
Thank you so much.
Thank you.
Thank you.
Thank you.
Have a good day.
All right, so now we're going to have our first giveaway of the afternoon. I've collected names and team numbers. So first, I'm going to be having a giveaway for $25 Go Builder. $25 Go Builder coupon. All right, can you guys share see my screen of the Go Builder website?
Yeah.
Okay, so first, the Go Builder giveaway. I have installed the name here, and here, I'm gonna give it a spin. All right, so the winner of the $25 Go Builder coupon is team 7172. If you could please type in public chat about just to show that you're here, and then privately DM me your team number, team name, email address, and then your phone number just for contact. And then now we have another drawing for the gecko wheels. This is what it's going to be looking like. And I'm going to be pasting the exact same names, but I'm going to remove team 7172 since you guys have one already. And yeah, I'm going to give it another spin. Okay, so I'm pretty sure this is a new FTC team, correct? I think I know who it is. I can just DM them privately. Okay, so that's going to be the two drawing that's going to be happening right now. And then I'm going to have another drawing at the end of the session, and also a special drawing of a $25 Amazon gift card for anyone who have asked a question. So next, we're going to have Iron Rain to present again, and they're going to be presenting about Opencv Vision Pipeline from grip to testable implementation in Java with live previews on Dashboard.
All right, thank you. We're going to go ahead and get started with today's presentation, which is going to be about how do you go from testing out a pipeline in grip, which is a piece of software you can use to kind of visually drag and drop pieces of Opencv operations together, and how do you take that from something that you can just experiment with to something that you can run on a control hub or an expansion hub. So to start with, first of all, what is grip? So grip is a program that I think was originally designed for FRC, but it can also be used for FTC or any kind of Opencv purpose. It's a program that you can download and install on a PC. It just allows you to kind of drag and drop different pieces of Opencv operations together and chain them together kind of like you would in a block code type scenario. It's super easy to prototype with and allows you to just rapidly develop a pipeline. And the best part yet is that you can take that pipeline and then export it to Java pretty easily, which is what we're going to be going over. So if you want to follow along, I guess first go ahead and download grip. But after that, you're going to have to set up FTC Dashboard in your Android Studio project. And that's going to be for looking at mainly camera previews and messing around with live configuration variables. So you can see on the right here how it says configuration. All of the variables in here and the PID coefficients are all editable. So on the fly, you can change one of these values to something else, and it will reflect in your code. So that's super useful for debugging, or what we're going to be doing is for using it to look into different stages of your vision pipeline. And it's not shown here, but you can also see a camera preview over here. That's what we're going to have. And if you want to, you can graph out any numerical variables as well as look at them in the telemetry. So after you have FTC Dashboard set up in your Android Studio project, all you need to do is install Easyopencv. So if you head over to their GitHub page, they have pretty comprehensive setup instructions that just make it pretty easy to get going with it. The reason you would use Easyopencv over the traditional approach is just that Easyopencv is, like the name suggests, very easy to use. It also allows you to, with pretty minimal setup, run your pipeline in a separate thread. So meaning that you can run your main op mode and your vision pipeline in separate threads at the same time, so that one isn't really slowing down the other. And so that you have fast feedback for your drivers if you want to do some type of teleoperated vision processing. Okay, so with all that being said, let's actually get into how to use grip. So here I have grip open, and I just added a source, which is an image. Here I just took a picture of one of our FTC cones that we went over in the last presentation. And so we need to chain together different operations to somehow get from this cone to an XY position that represents the center of this cone. So the first thing that we're going to do is blur the image. And the reason for that is eventually what we want to do is detect what's called a contour. And that's just going to represent kind of the outline of this cone, the boundaries of this cone versus the background. And so to do that, just to keep things clean and crisp without a lot of noise or variation, a blur will kind of work to wash out some of the tiny variations in the image and make it easier to detect just large blobs of color. So if I search blur here, all I did was click the blur node, connected this image node to the input of the blur node. And when I click this eyeball button, you can see this is the output of the blur. Right now, it's not doing anything because my radius is on 0. If you guys know anything about blurs, the radius represents kind of the neighborhood of pixels that are being averaged together to produce the new pixel. So for example, when I drag this radius out to, let's say, 27, I think 16 looks, 24 looks about good. What this is doing is for each pixel in this image, it's taking a neighborhood of pixels that is 24 by 24 wide and taking the average of all those pixels and making that the new color. So it's kind of averaging out the entire image to make it less clean, but easier to detect for contours. And after that is going to be our main step, which is the Hsp threshold. So for those of you who don't know, a threshold is just any type of operation in computer vision that can output a binary image. And what I mean by a binary image is just an image that consists of only white and black pixels. So you can see here, without changing any of these hue, saturation, or value sliders, I'm getting an image that is completely white, meaning that I'm letting all of the pixels through the threshold. A threshold is, you can think of it as kind of like a filter, where I'm saying for each pixel in the image, decide whether to let it through the filter. And the pixels that are let through the filter are white, and the ones that aren't are black. And when I go to mess around with these sliders, you'll see that I only let a certain subset of pixels through. And I only want to let the pixels through that are part of the FTC cone here. But before we get to that, first of all, some of you might be wondering, what is exactly hue, saturation, and value? So if I come over here to my slides, I have a graphic that you can try to use to visualize what each of those components do. So HSV is just another way of representing color, like RGB. Formerly, it's called a color space. But you know, traditionally, computers represents color with RGB, just 3 different channels of red, green, and blue light. And any combination of those types of light can produce any color, theoretically. But when it comes to how we think of color, I think HSV is a bit more realistic in that we kind of think of hue as the type of color. For example, if I just say orange or yellow or cyan, what I'm referring to is the hue of that color. And then the saturation would be how intense that color is. For example, something like hot pink would be very intense, or neon green over here. But something not very saturated would be somewhere in this inner wheel, something like pale, like a pale green or a pale purple. And this is the reason we would use something like HSV over RGB is just because it's a bit easier to tune, which is what we're going to be doing today. So instead of having to mess around with 3 completely separate, kind of unrelated channels, HSV offers a structure where you could just, first of all, tune your hue, right? So we want only like a green kind of hue to come through. We want a pretty high saturation to come through because we know that our cone is a lot more saturated in terms of its color compared to the kind of dull gray background. And we want a pretty high value to come through because the cone is pretty bright compared to the background as well. All right, so we can add, with that being said, we can come over here and drag the minimum requirement for the hue. So you can see as soon as I do that, we're immediately only letting through the pixels that meet our hue requirements. So what this is doing is it's saying for each pixel in this image, only let the ones through the filter that have a hue between 32 and 78. And 32 and 78 would correspond to some portion of this circle that we can think of as the hue wheel, right? So somewhere over here. In terms of saturation, like I said before, we want to have a pretty high saturation. Okay, so you can see the further out I drag that, the more saturated pixels are being selected. But I think something around here will give us all that we need to detect the cone. And then in terms of value, they shouldn't matter too much, but I think you can see as soon as I drag the value slider up, the black pixels on the top of the cone, as well as in the hyperbolic cutouts of the cone, they seem to disappear because a low value would correspond to something that's closer to black, right? And a high value would correspond to something that's fully lit. And when okay, so that seems pretty good. We have a bit of weird, okay. Yeah, I think that's good enough. All right, so now we have a image consisting of only black and white pixels, but how do you go from that to the exact XY position of this cone? You can do that using what I mentioned before, which is contour detection. So if I search find contours in here and click that, I can then drag this output into the input of find contours. When I hit the eyeball, I should get, I don't know why it's kind of messed up here, but you can kind of see just a faint line going around the entirety of the cone. So if I come back to my slides, I have a slide over contours. If I didn't mention it before, contours are just kind of boundaries that define shapes and forms in an image. So for example, if you ran contour detection on this image of a bunch of cards, you would be detecting contours on each of these cards because that's where there's kind of like a boundary between the card and the background. You could also be detecting contours here, but I think the way that they've tuned their contours, it only detects the kind of large ones. So once we have that going, we can't really go anywhere more in terms of just using grip because grip doesn't have the precise tools you need to, the code, I guess, or the nodes to detect the X and Y of this center. But what you can do here, I don't know if this is visible in the screenshot, but if you go to File or if you go to Tools and hit Generate Code, you can select Java as the language, and I'm going to name this something like Opencv Pipeline. And I can select, for example, just for desktop to save the file. When I hit OK, and I open my File Explorer, I can go ahead and see what type of code that this generated. Where exactly is that? I think it might be in a different one. Yeah, okay, there it is. Right. So you can see in here that this file is kind of importing everything that you need in terms of Opencv, and this method right here, process, is the main method that would be being run. You can see the different steps in here, like the blur, the Hsp threshold, and finally the contour detection. And so this is something that you can almost just directly copy and paste into your Android Studio project. And I have done that in here. Let me go over to my Android Studio. So in here, I have a file called Freight Frenzy Pipeline. And what I've done is I've just kind of copied and pasted what we had there and made a couple changes. Notably, we need this pipeline to be able to work along with Easyopencv. And so they provide a class called Opencv Pipeline that I can extend. And this is an abstract class that has a method that you need to implement called process frame. So this is basically what the process method was in the grip generated Java file. So I just renamed it from process to process frame. And you can still see the blur, the Hsp threshold, and define contours operations. But I also have this other section of code right here that I added. And what this is doing is it's allowing us to take a list of contours that we found and pick out the biggest one, right? Because in my contour detection, let's say I detected the cone, but mistakenly there was some tiny piece of green in the background that also got detected as a contour. I only want to keep the cone detected. So what I'm doing here is I'm looping through find contours output, which is just an array list of mat of points. A mat of point is how Opencv represents a contour. I think you could think of it as like a matrix of points. But anyway, I'm looping through this, and for each index I am getting the contour that is at that index. I'm computing the area of that contour because I want contours that are greater than a certain area, because I don't want to mistakenly pick out a patch of green that isn't actually the Ftc cone. So if that contour area is greater than some minimum threshold and that contour area is greater than the largest area that we have found so far, I'm computing the X and Y of the center of that contour, which I'll kind of get into in a moment, but I'm also keeping track of the X and Y of the largest contour that we found so far. So you might be wondering what this is doing over here. So I'm calculating what are called moments on this contour. So if I go back to my slides, I have a slide over exactly what those moments are. So in computer vision, when we talk about image moments, this looks a bit intimidating, but really all it's doing is you can think of an image as kind of a function that's taking an X and a Y, right? And it's outputting the intensity. That's what I stands for, the intensity of the pixel at that location. So for example, in this image, if I just took a black and white image, right, this would be an intensity of 255. Everything that's white and everything else would be an intensity of 0. So it's taking that intensity times X to the power of I times Y to the power of J. When we compute moments subscript 1, 0, all we're doing is summing up for all of the X's in the image and all of the Y's, X to the power of I times Y to the power of J times the intensity. So when we come over here and look at exactly what 1, 0 is doing, that's just the sum of X to the power of 1 is just X. Y to the power of 0 is just 1. So it's just X times the intensity. So really all this is doing is just doing a weighted sum of pixel intensities divided by all of the pixels. So what you're eventually getting is just the X position, the average X position of all of the pixels and the average Y. And that's exactly what we need for a contour, right? That's exactly what we need to get the XY coordinate of a contour. And so that's why I'm performing these moments here. This is how you do it in Opencv. And so when I have that X and Y finally computed, I can go over here and say that if I have detected a contour, right, if the index of my largest contour is not -1, right, because it starts at -1, if I found some type of contour, that index is going to be either 0, something from in the range of 0 to the size of our find contours output list. So if I have found a contour, I'm going to go ahead and draw it and draw a marker at that XY location and draw the contour as well. Then I have some utility functions here like handle dashboard and get position and stuff like that. All it's doing is allowing us to send stages of the pipeline over to dashboard. So I set up that dashboard here in the constructor, but when I call handle dashboard here, I'm actually picking out a pipeline stage, right? So before I go any further, let's talk about exactly what constants is. So this file is a config file. It's what dashboard uses to figure out what types of variables are your configuration variables, right? So when I talked about these variables over here that you can edit on the fly, these are the variables that I'm talking about. So you can edit all of these in dashboard as long as you specify @config on top of the file as an annotation. So we're going to be able to change that pipeline stage on the fly. And as we see that change, we can send either the blur input output, Hsp threshold output, or the contours output. And the specific code for this is available on our GitHub. If you want to clone it, check it out, make any modifications, it's all there. So all this is to say that now we can finally go ahead and test out this pipeline. So over here, I'm connecting to dashboard. I think the robot might be powered off right now. Nope, it is on.
Wrong IP address. Okay, so now we have FTC Dashboard. And this is, again, what I referenced in the slides. So here I can go ahead and select our example detector op mode. And when I hit init and I hit start, we should see, okay, so this is what our robot is looking at. It's looking at two FTC cones, one of which is red and the other of which is green. When I come into constants, you can see all of the constants that I defined over here in our constants.java file. So I'm going to X that out. In constants.java, you can see even our pipeline stage is right over here. So remember, I said that pipeline stage can be used to, we are switching over pipeline stage in Freight Pipeline. And that's going to allow us to send different portions of our, different stages of our vision pipeline over to dashboard. So when I go ahead and change this to 1, now we can see the blur stage, right? So after the blur, this is what's happening. And after the blur, we had an Hsp threshold, right? So after the threshold, this, okay. I think the robot just shut down. Should restart in a second. But what I was going to say is if I change this to 2 and then 3, you'd be able to see our robot's Hsp threshold output as well as the contour detection. So, okay, it's getting set up over here. All right, so again, here we have the blur output, then the Hsp threshold output. So you can see just that the green part of the cone is being detected. And I think this blur is kind of high. Remember, if I want to, I can change the blur radius if I want. So I can move this down to maybe 5. If I change it down to 1, you get the original image, right? So this is the advantage of having using FTC Dashboard, is that you can change variables that you want to on the fly and immediately see their effects. Okay, so let's go back down here. So that's, okay, this is the output of the Hsp threshold. And then finally, this is contour detection. And that crosshair that you see right there is the X and Y position that we computed using image moments. And so, yeah, that's how you go from grip to finally detecting this XY position. And then to use this on the field during Auton, since you have X and Y, you could do something like if the X is between 0 and some range over here, then it's on the left. If it's between this range and this range, then it's in the middle. If it's higher than a certain threshold, then it's on the right. And then from that, you can go ahead and run your different op modes, or not op modes, but you can run different sections of your autonomous accordingly. All right. I think that's going to be it for the presentation. If you guys have any questions, you can feel free to ask them.
Okay, thank you so much, Irene. That was a fascinating presentation. Love it. And then now, if you have any extra questions, make sure to drop them in the chat, and I'm sure Irene will be there to answer them. So next, we have Hank from Area 52 will be presenting about vision targeting and how it helped Team 18227 in their last season ultimate goal. Welcome, Hank.
Can you see my screen?
Yep.
Okay. So vision targeting in ultimate goal. So I'm Hank Chen. I'm currently a programmer on FTC team 18227. This is my second year in FTC, and I'm going to Rice Middle School as an 8th grader, and I've been in FLL for 2 years before that. Okay, so agenda. So we're first going to talk about like what is computer vision, and then after that we're going to I'm going to explain why computer vision is important in FTC and like why you should use it, then how we used it for high go detection, and then auto aiming with PID and Opencv. So what is computer vision? So by definition, computer vision is a field of artificial intelligence that trains computers to interpret and understand the visual world. Using digital images from cameras and videos and deep learning models, machines can accurately identify and classify objects and then react to what they see in those contents. computer vision works somewhat like human vision, but human vision is actually probably better sometimes because humans have had like lifetimes of context to know how far things are away from each other and whether they're moving and what the or image is depicting. But computer vision trains machines to do these same things, except with data algorithms and cameras instead. Computer vision is pretty common in like your everyday life. Like if you have an iPhone, there's face recognition on your phone. That's possible because of computer vision, crowd detection, human like suspicious behavior detection, and there's illegal parking, speeding vehicle detection, and many, many more. So why should you use computer vision in FTC? So computer vision is usually one of the most important aspects of doing good in FTC. So this is largely because FTC challenges usually have some sort of object detection. Last year it was shooting rings, like before that in Skystone you need to detect like the blocks. So most, if not all, top teams use computer vision or some sort, since most of the challenges need like this. So computer vision is also not really that hard to set up and use. So if you want to use it, it's definitely worth using it if you want your team to like improve from last year. Our team used computer vision pretty effectively last season when the challenge was centered around like shooting rings, going to different areas, wobble goes. So without using computer vision to identify like the high goals and ring stacks, our team would like do pretty badly compared to what we actually did. So computer vision, an example of like it being really important was Skystones and to deck the blocks and then stack them on top of each other. We used computer vision this season in Opencv mainly to identify the goal and then lock the ring launcher onto the goal in ultimate goal. And I think we did pretty well since we got 7th in Texas Cup. So yeah. So how we did high goal detection using Opencv. So high goal detection was really, really important last season since we needed to shoot rings into the high goal as fast and as many as possible, and that would also be accurate if you wanted high points. So our Opencv pipeline can capture multiple features of the Go tower with various thresholds of color and shape combinations and pixel level. So to do this, we use Opencv through an app called Grip, which has kind of already been explained before that. So we like got an image of the high goal. Then we put into Grip, we tune the colors, which is the Hsp filtering, the shapes, contours, the noise detection, which was erode, the hue and saturation values. After doing this and like getting it to like work, you had to like generate code through Grip and then adjust to our OP modes from Android Studio. We also decided to make the parameters tunable through Ftc Dashboard with camera previews as a daily routine. We did this because it's like much more efficient to tune the values from there. Since it's easier to change the values, it gives you like a camera view and you can tune all your values from one place. So after like the second iteration, the high goal could be detected in like only 0.1 seconds. This is pretty fast and accurate. So what we did is we used the high goal detection after to auto aim, which would be explained like in 3 slides. So to help with auto aim, we actually drew a green bounding box around the goal with Java and Android Studio to help it serve as a sensor input to PID. False positives and multiple features cross-checking. So what is a false positive? So in this case, a false positive in object detection is something that should not be identified as the target, but like tricks your algorithm. So in our case, the false positive was people with red/blue t-shirts on our team and in general that distracted our Opencv pipeline. So to fix this, we actually had to add detections of the white logo in the middle and the red/blue columns below the high goal. So even if like someone with the red or blue shirt was in the camera, it wouldn't be distracted. So we intentionally had someone dressed in blue and red to test our second iteration of this detection algorithm. We also cross-checked other features to ensure other factors didn't screw up our auto aim, like lighting, for example, and the other Opencv pipeline features like the values. Auto aiming with PID in Opencv. So before we look into like how we use PID in auto aim, we have to cover what PID is. So PID, or proportional integrative derivative, is basically a controller algorithm where it takes like the difference between the target you want it to go to and the sensor inputs, which is the error in this case. So it's a control loop mechanism that employs feedback. It's widely used in industrial control systems and a variety of other applications. So PID control provides a continuous variation of output within a control loop feedback, which removes oscillation, increasing process efficiency. So PIDs is pretty important FTC for many reasons. An example of this is just driving straight in auto OP so that your like robot path isn't messed up, since PID corrects it, makes sure the robot goes straight. But for this case, it was that we needed to be able to accurately turn the turret of the robot onto the high goal that was already identified by our Opencv pipeline. So auto aiming with PID. So we use computer vision through a mounted camera to identify the high goals first, which then basically provides the sensor input or error to a PID with the X coordinates of the bounding box we draw around the target. So by mounting the camera like on top of the shooter, we know like we expect the target to always be in the center of the camera image. So our Opencv pipeline is constantly updating the bounding box of the target from the camera view, and the streaming is like 15 frames per second. So by constantly reading the bounding box X position, which will be updated by our Opencv pipeline in real time, we know where the target is on the screen. So we can calculate the correction. Well, PID will calculate the correction. So we can find the distance from the target, which is the middle of the camera image, by subtracting the X position where the turret is aiming from the center. And then we just input this as our error for PID. After finding the error, what the PID algorithm does is it calculates a correction based on how our KP, Ki, and Kd coefficients are tuned. Then we apply the correction to our bearing servo, which then turns the shooter. Our first iteration, like I actually used a red ping pong pad and a webcam mounted on a rev servo to mock the actual target / high goal. So only after the first iteration, I moved to like the actual turret on the robot. So then we had to scale all our PID values, but in return, the response time was much faster in turning. So how did we tune the PID aiming parameters? So getting and running auto system requires like a lot of PID value tuning. So in our first iteration, the PID took too long to like turn to the target. So as a result, I had to increase KP, which would make the turning faster, and then a little bit of KI. So just in case, like if the KP turns really close to the target, but can't eliminate the final like small gap, which is a common error in PID, which can be fixed by KI. So after the first iteration, our PID was now like too sensitive and fast while the chassis was moving around the target. So for this, I decreased KD, which would make the aiming less sensitive. So after the second iteration, our aiming was actually really accurate and good, until we found out that the turret was like, the overflow of KI was causing the aiming to go crazy after some time if it didn't like detect the target. So I decided to set a forgot factor. So the forgot factor basically just sets a limit on how long the KI's memory is. After the third iteration, then our aiming was like extremely accurate and quick, only taking around 0.1 seconds to walk under the high goal. This is like a video presentation of last season. Yeah, so this is iteration 1 I use, just basically, yeah. And then as you see on the left, that's dashboard and like the Opencv, like trying to lock on to the high goal. So iteration 3 is when we tune KI and KD. So in result, the aiming is like really responsive and quick. And we also added this feature, as you can see, the LED light is like blinking according to how it is. So yeah, so this was just in case the goal got out of like our camera. So we added an Intel T265 to like help with that, to get like the camera turned back on track. Okay, so yeah, that's the end of my presentation. If you have any questions, either put in the chat right now or email that.
Okay, thank you so much, Hank.
I'm just gonna stop the presentation. If you have questions, just put in the chat and I'll answer.
Okay. Next up, we have Isaac and Michael, both from Team A565 TechnicBots. They will be demonstrating and giving us all an introduction to Roadrunner Simulation, a motion planning library written just for Force Tech Challenge, and it is designed mostly for autonomous movement. Welcome, Isaac and Michael.
So welcome to our Roadrunner Simulation introduction, aka Meet, presented by TechnicBots A565. My name's Isaac. I'm in 8th grade. I go to Rice Middle School and I like playing video games.
Hi, I'm Michael. I'm in 8th grade and I also go to Rice Middle School and I like food.
So we're gonna go over what is Roadrunner, different Roadrunner simulators. We're gonna go over like what Meet looks like, what it can and can't do, how to install it. We're gonna go over APIs, and lastly a demo.
Roadrunner is a motion planning library designed primarily for autonomous robotic movement. It allows for complex path following and generation while maintaining control of velocity and acceleration. This enables bots to have more accurate and advanced path following capability. Roadrunner uses odometry, also known as dead wheel sometimes. Odometry refers to the use of sensors to determine a robot's position. Dead wheels are unpowered omni-wheels not connected to any motor. These wheels have rotary encoders to track distance travel. This was discussed during the presentation of 18175 about odometry.
So what are different Roadrunner simulators? Well, there's gluten-free's FTC simulator, which is more towards the realistic side. But like Meet is like a path visualizer, which is based on path points, while gluten-frees can simulate like pure pursuit, which is close to Roadrunner, but because like it loosely follow like path points determined, loosely follows a path determined by a set of waypoints. So this is what Meet looks like. Basically, you have coordinates based on this coordinate plane. And basically, this is the new Fright Frenzy map. And you have the X towards the horizontal plane, and then Y as the vertical plane. So, Michael, you do this.
Meet can visualize paths, but paths and path points you specified, and it can simulate velocity trajectories and other stuff, but it cannot simulate obstacles in physics. Because it can give you path points and trajectories, this is very good for brainstorming and discovering new paths using Roadrunner. Meep can't actually simulate stuff like gluten-free simulator, but it can be very good in the early season for brainstorming. This can be useful because in the pandemic you might have to social distance yourself, but you can still work on Roadrunner remotely.
So how to install it? Well, first, so the Roadrunner Quick Start is not required, but it's pretty helpful because it has a lot of Roadrunner dependencies. So like you can like clone this and then have the dependencies. So this is what it will look like when you like clone it or like import it. And so this is the Meep GitHub. There's like a lot of resources on here. There's an installation video you can look at. So basically, first step, you want to create a new module, and then select Java or Kotlin library. And you can select testing. And then give it a sec to load. So once that loads, there should be a Gradle here that's named after the module named Meep testing. Yeah, so after this is implemented, you have this, which then you can change the Gradle, or you can, wait. Okay, you can copy this directly from the GitHub. And then paste it, and you should be set. You can sync it, and it should be ready for you to code. So once you go into Meep testing, you have a class, which then you can rename it for like Meep testing. And you have like, so on the Git, you actually have a sample code which you can just directly copy and paste to test. And if you want to test it, then you need a new configuration, which by selecting this, and then choose application, select this because you created the class. Maybe testing down here, and then create configuration. And you can name it, it's just Meep testing. Apply OK. And then you should be able to run it. Yeah, it should load here. And to get the Fright Frenzy, you can just change this to like Fright Frenzy. And that's basically it for the installing. So yeah, you can just like watch the installation video if you didn't understand what I did just now.
So a robot's position is uniquely specified by pose, which gives you your x coordinate, y coordinate, and a robot heading, which is the angle the robot is positioned at. In trajectory builder, we have trajectory, which pretty much is like the path the robot's going to take. Then we have trajectory builder, which is where we actually put in all the like instructions. And the first pose right there is where the robot's going to start. And right now it's just going to start at 0, 0 with an angle of 0. And you can just have the robot to move forward using dot forward and then a number. I think that's in inches. And then there's backwards, which is back. And then line 2 lines to a position on the coordinate plane using a vector, which is x and y. You can also combine it with a heading. This is spline, which is a piecewise function that you can use. It's sort of like line 2, but what makes it different is that you can add waypoints, so your robot can hit different points along the coordinate plane while traveling to your final destination. You can go left by strafing left, strafe to a position by, it's sort of like line 2, again, just a vector. And here's a Freight Frenzy path visualization demonstration.
So basically, this is what it looks like when it's running. The blue lines simulate what your path is. So some like key points in my code are like, for example, spline 2. Basically, this is the position you want to go to, your vector. And then you can set your heading with this. Let's see. Yeah, as I said before, like this is like coordinate plane. You have your coordinates, like I set to minus 1143. That's like right here. Let's see. Yeah, that should be some key points in like Roadrunner APIs and how it's like simulated. Yeah. So any questions?
I think Meep, it's more of like for path visualization, and it can also be, I think it's like easier than using gluten free. Gluten free takes some setup. Yeah, it takes some more setup. And it would have to account for more details.
Okay, if you guys have any further questions, just drop them in the chat and Isaac and Michael will be there to answer them. So next up, we have Daniel. He's from 8565 and he's also a freshman at Shepton High School. This is Daniel's third year in FTC and he's very passionate about robotics. He's going to be talking about FTC linear slide, counterbalance springs, and different linear slide spool sizes. Welcome, Daniel.
So this is the FTC linear slide presentation. And yeah, as he said, we're going to be going over linear slide, counterbound spring, and the spool size in linear slides. So let's get started. I'm Daniel Tower. I'm a 9th grader at Shepton High School. And in my free time, I play clarinet. I do 3D modeling and make 3D animations. And I also like playing video games. For the agenda for today, we're going to be going over what a linear slide is, the different types of linear slides, how a linear slide works, the counterbound spring in certain linear slides, and spool size calculation. So what is a linear slide? Linear slides are linear motion mechanisms that expand and retract in one direction, and they're very commonly used in FTC. The last year's, well, for Skystone and Rover Ruckus, both linear slides were both necessary for those 2 seasons. How does a linear slide work? Basically, linear slides are made up of a series of connected slides or stages, all wrapped together by a string, and in certain cases, by a system of strings going in a zigzag pattern. And as the length of the strings shortens, the linear slide expands upward to make up for the lost string. For the types of linear slides, the 2 main types are cascading and continuous. With cascading linear slides, each string is strung to the next slide, as you can see in this image down below, and all of the slides move at the same time, as opposed to continuous, where only one slide moves at a time. And for cascading, it's slightly faster than continuous stringing, but requires lots of torque and is less precise because all the slides are moving at once. And a benefit to it is that it has a constant force on the motor, unlike continuous. And for continuous linear slides, the string is wrapped around the slides in a zigzag. So as you can see in this diagram, as the string is shortened, the linear slide will have to expand to make up for the lost string that's wrapped around the spool. And yeah, only one slide moves at a time. So it's slower than cascading stringing, but it's also a lot simpler. Like as you can see with continuous stringing, you only need one string as opposed to cascading. And because linear slides can only move in one direction, they can only expand, but they can retract. They can't only rely on gravity. So a return string is necessary to retract the linear slide. And usually this is done by having a spool with one side having the string to expand it and one side having the return string, as you can see in this. So in the diagram, as the red string shortens, which means the linear slide will expand, the yellow string is moving in the opposite direction. So the yellow string will be loosening to make up for the linear slide expanding. And as the red string expands, which will retract the linear slide, the yellow string will shorten, which will help pull down the linear slide because it can't only rely on gravity. For the types or the materials for linear slides, there's extrusion slides, drawer slides, and ball bearing slides, which we'll go over in the next slide. But extrusion slides are made up of a stack of extrusions sliding against each other using bushings or V-wheels between extrusions to slide smoothly. The black plastic piece in this bottom diagram is an example of a bushing, and extrusion slide kits are sold by the main FTC vendors like Rev, Actobotics, and GoBuilda, and it's usually the cheapest option. There's also drawer slides, which is the same style of slide that's used in drawers at your home. They can be aluminum or steel, although steel is a lot heavier. They're very smooth. They can handle more load than extrusion slides. And the main brands of drawer slides are Mizumi or Long Robotics. And for ball bearing slides, it uses ball bearings, hence the name, inside the slides for very smooth motion. As you can see in this example down here, this is a 3D model of a short telescoping Mizumi ball bearing slide. And the ball bearing slides are much more lightweight compared to drawer slides, but they only come in fixed lengths and are very hard to cut. And the main brand of ball bearing slides is Mizumi. So as you can see, it's made up of 3 components, the 2 outer ones and the middle component, which slides between the 2 outer components with ball bearings for smooth motion. Next, we're going to talk about the counterbound spring. So a counterbound spring is not just specific to linear slides and FTC, but in general, it's a spring used to help lift and support heavy loads. And for FTC, it's often used in one-sided linear slides where only one motor is controlling one side and the other side is being controlled passively. And counterbound springs can come in constant torque or constant force variants, which we'll talk about in the next slide. Here is an example of the Technicbot, us using a counterbound spring for a linear slide in the Skystone season. So as you can see, this counterbound spring is helping the linear slide to expand upward. It's unraveling, and when it goes back down, it rewraps itself. And Vulcan Spring is a company that makes counterbound springs like the one you saw in the video. They have a big lineup of springs, including constant force and constant torque springs. And they can also sponsor your FTC team if you ask nicely, which can get you a couple free springs from them. Here's just an example of their constant torque spring. They have a wide variety of different amounts of spring torques, which also have different thickness, widths, and all of this. And next, we're going to talk about the linear slide spool. So the spool size of a linear slide affects the torque and speed of the slide. So the bigger the spool, the less torque and more speed it will have. And the opposite is also true. The smaller spool, the more torque and less speed the spool will have. And if the spool has more torque, it can lift more weight, and the opposite is also true. Here's just an example spool CAD model that I made in Blender. And spools are pretty easy to 3D model if you know how to use your 3D modeling program. This one was just a cylinder with the faces extruded and scaled a couple times to create this spool-like shape. And then I just beveled the edges and used a Boolean operator to cut holes for the axle and screw holes. So it's relatively simple. Next, we're going to talk about the spool size calculation using the JVN calculator, which is an online calculator. It's usually in like a Google Sheet or an Excel file used for calculating the gear ratios necessary for a system, but it can be used for almost any mechanism on the robot. Like they have modes for linear mechanisms, drive trains, intakes, and it just calculates the necessary gear ratios you need for the system, depending on what you want. And this calculator was originally made by an FRC coach, but it applies to FTC too. And to use it, you just plug in values like the motor specs. Some you can just choose a motor and it will have all the specs for you already. You put in that, the gear ratio, travel distance, the load, the applied load, the amount of weight on the linear slide in this case, and the pulley or spool diameter of the linear slide. And then it will run the math and give you the linear slide speed and the time it takes to fully extend or retract, depending on if there's a load or no load, which you can see over here. And here's just comparing two different types of spool sizes. Everything else is constant in these two, except the pulley diameter, like the load is the exact same, the motor, the gear ratio. And as you can see, the pulley diameter will affect the speed, but the one with the smaller pulley will have more torque. And then I also tested it in real life with this benchmark test setup. So 5 pounds of weight was added to the lift for this. And then the time it took for the linear slide to fully extend was recorded. And in the software, the motor was set at nearly max power for the tests. So here are the results of the tests. This is comparing the results of what the JVN calculator said versus reality. And these values are rounded a bit. They weren't exactly the same, but for the 2-inch spool size on the JVN calculator versus reality, they were pretty close. Again, this is rounded, and then with the bigger spool size, the calculator was only off by 0.15 seconds. And this shows that the results of the JVN calculator are very close to the real life tests. So when you're making a linear slide and you want it to go at a certain speed and you don't know what spool size to use or which motor, then you could plug it into the JVN calculator. Here's just the results using the bigger size spool, the 3.5 inch. And this is just showing how extra weight on the linear slide affects the time for it to fully extend. Any questions?
All right, thank you so much, Daniel. If anyone has any questions, just put them in chat and Daniel will be there to answer them. So we're here for our second giveaway right after the next presentation by Adrian. This giveaway will be a $25 coupon for shopping at AndyMark. Again, please make sure your team number is attached behind your name so you can be automatically entered for our next giveaway. I will be, again, taking a screenshot of the entire participant list while Adrian is presenting. And after our $25 Go Build AndyMark coupon giveaway, we will also be having a $25 Amazon gift card. And people that are entered already are the ones that have already asked a question. So yeah, that's the second announcement. And next, we're going to be having CNC routing with Fusion 360 is shown and demonstrated by Adrian from Technibots 8565, and it is Adrian's third year in FTC. Welcome, Adrian.
Okay, so this is what is CNC routing and how to use it with Fusion 360. Okay, so I'm Adrian Lin. I'm 13 years old. I'm an 8th grader at Curtis Middle School, and a few hobbies I have besides robotics are cello and taekwondo. Okay, so today I'm going to be going over the basics of CNC cutting, how to use it in Fusion 360, an example of where you can use CNC cutting from the Rover Ruckus season, a live demo, and then a few tips and tricks. So what is CNC cutting? Let me know if you guys can't hear the video.
Oh, Adrian, I don't think we can hear them.
Okay. Okay.
Hi there, and welcome to another episode of Maker 101. I'm Michael.
And I'm Brooke, and this is Maker's Workshop. Today we're going to talk about CNC routers.
A CNC router is a machine in the class of precise computer-controlled equipment. The tool head is a spindle which holds a radially symmetric cutting implement called an end mill, also called a bit. By spinning this end mill very quickly and controlling the path the end mill takes, you can cut away from and therefore shape blocks of wood, plastic, foams, or metal.
Another way to think of it is just a hand router, but on a CNC machine. You can control X, Y, and Z directions, and you can accomplish much smoother and more complex shapes with near perfection. Very simplistically, the parts of a CNC router are 1. The gantry, which has motors and a timing belt set up to control the X and Y position of the tool head. 2. The tool head, which has another motor to control the Z direction or the height of the spindle. And 3. The spindle itself, which is the part that holds the bits and the spinning joint.
The gantry is usually on top of a fixed plate or frame where you put your material. To secure your material on the fixed plate, you have clamps or vacuums depending on the particular machine. To clean the dust generated from cutting, there is usually a network of vacuums to suck it up, or a cover of some sort over the whole machine to keep the dust contained.
The main variation in CNC routers is the material and number of dimensions of control. There are CNC routers that are made to cut metal, but most are made for woods, plastics, and foams. Most CNC routers control 3 dimensions, X, Y, and Z, allowing you to get cool surfaces and shapes, but you can't make overhangs and convexities on your CNC parts. There are CNCs that have a 4th axis that actually rotates your material along one axis to get another orientation. These can allow you to get overhangs along that axis of rotation. Some very complex CNCs have 5th and even 6th axes, allowing you to create virtually any shape. The only limitation is that you can't create closed hollow shapes, like an empty ball, for example.
All right, but how do I design for a CNC router? CNC routers require a special file type called a G-code file. You can make these files by 3D modeling your final part, setting up how big your initial stock material is, and then telling the 3D modeling software the cuts you want to make to get your final part. Generating G-code can vary from easy to difficult depending on how much control your software gives you and how complex your final design is.
If you're making a box, it will likely be easier than if you were trying to make a chess piece, for example. If you are using a computer-aided design, CAD, software to make your parts, you should make sure the software also has computer-aided manufacturing, or CAM software, in order to generate these G-code files.
Another thing of note is that G-code files are special to each CNC machine, make, and brand. So you need to make sure you have the right software to generate files for your machine.
Some things you'd want to specify as parameters when making a G-code file is the speed of the spindle, the gantry's traversal speed, the density of the material you're cutting, and the types of end mills bits you are using. In addition to getting end mills with different diameters, you can also get them in lots of different shapes to make cool cuts. We're working on another Maker 101 video that'll be coming out soon, diving a bit more into this topic.
Hi there, and welcome to another episode.
Okay, so now how to generate the G-code. So in Fusion 360, you would first want to create a setup which is going to contain all the operations. After that, you can add the appropriate operations to your model. So a few examples are bore, which is used to create holes, 2D contour, which goes along the perimeter of your entire model, which cuts out the entire piece, and then engrave, which just engraves a design onto your model. After that, you can then generate and then export the G-code to your CNC machine. So tool settings. So the main tool setting is spindle speed and how fast the spindle is moving. So whenever you first get a CNC machine, you will first want to research and figure out what other people have done to figure out what speed or how fast the spindle should spin. After you've done a few tests, if the spindle is getting too hot, you would know that it's moving too slow or spinning too fast. And if the spindle breaks, then it means that it's moving too fast or spinning too slowly. And this is going to be different for every machine and material. So the sorting mechanism. The main goal of the sorting mechanism is to just separate the cubes from balls by exploiting the size difference. So the balls are about 2.85 inches in diameter, while the cubes are only 2 by 2 by 2 inches. So because of this, the balls will not be able to fit under the overhang, so they'll be forced to follow the path, the curved path, and exit out the side. And because the cubes are smaller, they'll be able to fit under the overhang and exit out the front. Okay, so what part should we CNC cut? There are two parts to the sorter, and the first one is the top piece. So this design is much more complex, and it would be very hard for a CNC cutter to cut out. In addition to this, it would take a lot of time and waste a lot of material. So because of this, it would most likely be 3D printed. On the right, this bottom plate would most likely be CNC cut because it's very simple and it'd be much faster than 3D printed. So live demo. Okay, so here's the model of the bottom plate. So first we want to create a new setup over here. Okay, so because this model is at a slant, we'll want to change the Z-axis over here. And then we want to actually select the model that we're going to be cutting out. There we go. And then the highlighted piece that you can see around the entire model is the stock piece, which is a piece that the CNC machine is going to be cutting out of. After that, you can click OK, and then you have the setup done over here. Okay, now that we have the setup, we're going to want to add the operations. So first is the bore, and this will just be cutting out all of the holes. So now we just want to select all of the holes. And as you can see, it's starting to draw in lines and arrows, and this just represents the path that the spindle head will be taking. Okay, now we want to select the tool that we're going to be using. Okay, so there are many different types of tools, but the ones that I'm going to be using is the 3mm flat end mill. So the diameter of the end mill is actually really important because if it's too small, it can cut really detailed work. It can cut a lot of details, except you would have to cut really slow or else the end mill would break. And if the end mill was bigger, you could cut out pieces a lot faster, except you won't be able to cut a lot of details. Okay, so now that we have the tool selected, all of these are actually the presets or the settings that have been set for this particular tool and machine. And now that's how you do the bore. You can see it pop up on the side over here. And now we're going to want to cut out the entire piece. So we're going to use 2D contour. So this one, we will want to select the bottom edge of the entire perimeter. The tool has already been selected. And then in order to reduce stress on the tool, we're going to use something called a ramp. So instead of the tool going all the way down and cutting around the entire thing, it's only going to go down around halfway to a third, go around while slowly lowering it, creating a ramp. So this will just make the tool cut less material at once, so it would reduce a lot of stress on the tool. That would help prevent it from breaking. Okay. Now that we have both of them done, we can actually simulate it. I want to select the entire setup, simulate, and then play. So you can see the tool head going around and cutting everything out. Okay, so now that we have everything done, we're going to want to generate and export the G code. So go create a new NC program. This is just the name. And then this is the folder that's going to be exported into. And then on the operations tab, make sure all of the operations and setups are selected. Now we can post. Okay, and now the G code has been sent to this file location. Okay. Okay, so here is the sorter in action. Okay, so as you can see, this black part on top has been 3D printed, and it's a little bit hard to see, but on the bottom, there's a clear plate that was CNC cut. Okay, so as you can see, the cubes are smaller than the are able to fit under the overhang, so they fly straight out, while the balls are too big, so then they have to go out of the side. Okay, so a few tips and tricks. So it's always recommended to have safety gear, like safety goggles to help prevent any flying pieces from hitting you in the eye, and make sure you have no loose clothing so that nothing will get caught in the machine. And it's always recommended to have a cover over the entire CNC router. So this is to prevent dust or any flying pieces from going outside of its area. And then never go touch or go near the spindle when the machine is on to prevent yourself from getting cut in case the machine turns on. And then for Fusion 360, always make sure you use the contour last. And this is because if you do it first, then the piece will be cut and fall out of the holds, and then it won't be able to cut anything else. Then always make sure you always use the appropriate tools in operations. So if you're trying to cut a hole, use bore and make sure you don't use contour or engrave. And then try using a ramp whenever cutting to reduce the stress on the tool. So this will just prevent your tool from breaking. And the only downside to this is that it will take a little bit more time. And then make sure that the tool settings are correct. So always do your research and use your intuition, and make sure you don't do any crazy numbers like 100,000 RPM or 5 RPM. And here are the credits. And are there any questions? Okay.
Adrian, I think there's one question in chat.
I'm actually not sure of the particular brand, but it's a pretty small one. If you want, I know John is in the beginner track and he should probably know the brand name.
Okay. If you guys have any further questions, just drop them in chat and Adrian will be there to answer them. So now we have our second and third drawing of today's session. So I'll be sharing my screen. So this one, the first one we're going to be having is a $25 Andy Mark coupon gift card. And here's going to be the team names, and I'm going to give it a quick spin. So we have team 11472. Could you please announce in public chat your first, and then DM me your private information about your team number, your email address, and basically your contacts. Okay, and then from the beginning of the track, I mentioned about a $25 Amazon gift card, and now these names are right here. These are the people that have asked a question throughout this entire track. So out of these people, one will receive a $25 Amazon card. All right, we have a winner. It's David from team 11472, and just privately DM me your name and your email. And I think that should be the conclusion of our track. So thank you guys, and thank you for the presenting teams here. And I'm pretty sure in the main session, there is a FGC track going on. Okay, thank you.